This is part 2 of Chapter 5, Practice Problems. We'll begin with 5.7. Name the following binary molecular compounds. These are different than naming ionic compounds, in that molecular compounds, instead of being a metal and a nonmetal, will be combinations of just nonmetals. The way you name them is also a little bit different. Most people find these easier than naming ionic compounds. So let's work through these two and have you practice them. A is NF3 and B is N2O4. A strategy here, each compound will be named using the systematic nomenclature, including Greek prefixes when necessary. So the first one will be nitrogen trifluoride. We have 1 nitrogen and 3 fluorines. You still name the first element outright, kind of similar to how you would name ionic compounds. And then you'll use mono, di, tri, and so forth. And most of these are pretty easy to remember since a lot of these match up with geometry, which most of you or all of you probably have had. The second one will have 2 nitrogens and 4 oxygens, so it will be dinitrogen tetroxide. So most of these are fairly straightforward. The key is just to remember the prefixes for 1 through 10 and then just apply it to your situation. To distinguish ionic from molecular, just make sure you look at it and can convince yourself that in the case of a molecular compound, there's no metals present. And then in an ionic compound, the metals first and the nonmetals second. There's 2 different naming conventions, so make sure you know the difference. One thing to think about is to make sure that the prefixes match the subscripts in the molecular formula, and that the word oxide is not preceded immediately by an A or an O. Instead of tetraoxide, it's tetroxide. And just with practice, you'll get the hang of when you drop the letters and so forth. Alright, so 5.8 will go the opposite direction. We'll go from name to formula. And just like with ionic situations, this is usually fairly straightforward. It's easier to go from name to formula in general. A, sulfur tetrafluoride, and B, tetraphosphorus decasulfide. So the key thing is to make sure that you know the Greek prefixes and what that means, how many elements it represents, and then just write it out using the abbreviations and subscripts. So strategy, of course, will be figured out using the systematic nomenclature guidelines, as I mentioned. The first one is SF4. And the second one is P4S10. Practice more of these, and you will get to in the homework, but practice even more if you can, just until you're comfortable with it. Alright, let's move on to the next example. This is example 5.9. We're going back to ionic compounds and throwing in polyatomic ions. There's a list of common polyatomic ions where you just have 1 positive charge, which is ammonium, and the rest are negatively charged. Key thing here is that the polyatomic ion, that whole group of elements, so for example, the sulfur, oxygen, all 4 oxygens, so the sulfur and 4 oxygens, this whole thing will have a charge. So it's a group of elements that'll have a charge. Treat it just like you would an anion that has either a -1 charge or -2 charge or -3. It's just the whole group will have its charge all together. Alright, so we'll just jump right into these. AFE2SO4 in parentheses 3, part B AL, and then in parentheses OH, and there's 3 of those, and CHG2O. Strategy here is begin by identifying the cation and anion in each compound. Pretty easy to identify the cation. It will be a metal, except for the case when you have ammonium, which is one of the polyatomic ions. But every other situation you'll have will be a metal first. Once you identify the cation and anion, then you can combine the names for each, and then of course given the whatever the name of the polyatomic is. So we'll just jump right in so you can see how this works. If you want to practice again, pause it, but if you're unsure, then just go ahead and keep watching. Okay, so for the first one, we have Fe2SO4 3. From the list of polyatomic ions, SO4 is sulfate. The sulfate will have a -2 charge, so the whole thing, S and all 4 oxygens, -2. Since there are 3 of these, this half of the molecule will be -6. So since this half of the molecule is -6, then the positive half needs to be +6. So to get the +6, and we have 2 irons, you divide 6 divided by 2, you get 3. So this would be an iron 3 sulfate. So this is combining the idea of not only polyatomic ions, but also multivalent transition metals. And again, as I mentioned in part 1, iron is the most common one that you will see. All right, let's look at part B. We have AlOH3. This is aluminum, and aluminum only has one charge state. You don't have to use a Roman numeral, so you just state aluminum. And this polyatomic ion is hydroxide. So aluminum hydroxide. Looking at the last one, this is not a situation where you have a polyatomic. This is just normal oxide. But you do have to deduce if it is which charge state of mercury that it is, because mercury is also another one that is multivalent, meaning it has more than one possible positive charge. The oxygen is 2 away from the nearest noble gas, so it needs to gain 2 electrons, giving it a -2 charge in its ion state. The mercury, Hg2, we need to have +2 to match the -2, so 2 divided by 2 is 1. So this would be a mercury +1. And the name is mercury 1 oxide. One thing that you want to take with you is that be careful not to confuse the subscript in the formula with the charge in the metal ion. This was also mentioned in part 1. So for example, the subscript on the iron is 2, but this is an iron 3 compound. It's not how many irons that you use, it's actually which charge state of iron is it. Is it iron 2 or is it iron 3? So the Roman numeral possibilities that go with iron will either be a Roman numeral 2 or a Roman numeral 3. Example 510, name the following. We have part A, BrO4-, part B, HCO3-, and C, H2CO3. Strategy here is looking at something that is either an oxoanion or an oxoacid. Identify the reference oxidation, meaning the one with the 8 ending, and then apply rules to determine appropriate names. So again, a lot of these are in the polyatomic list, and some of them are acids. The last one is an acid example. And there's really only a handful of these that you would need to commit to memory. And once you practice and see them and write them out a few times, then you'll always know what they are. So part A, BrO4- has one more oxygen atom than the bromate ion. Bromate is BrO3-. So since it has one extra oxygen, then you're going to give it a PER. So it'll be perbromate ion. In the next example, this is going to be stemming away from the CO3 2-, which is our polyatomic carbonate ion. We have one hydrogen added to that, and so you just state hydrogen. So this would be hydrogen carbonate. And in the last example, we have H2CO3. This does not have a charge anymore, so with the two hydrogens, we actually neutralize the polyatomic. And one other thing I want to mention is when you get a little bit deeper, one other thing that you can have that will be a positive charge is hydrogen. So hydrogen can be written as your first element in a situation with something like carbonate. And a lot of these will be acidic or slightly acidic. So here we have carbonic acid. So the first one would be hydrogen carbonate ion, and then with one more we actually are in the neutral situation, and this would be carbonic acid. And again, a lot of these are in tables, and as you work with them and see them a few times, then you'll have them committed to memory. And then one thing to think about is just to keep track of your charges and if it's neutral or if it's charged and so forth. So here are some common polyatomic ions that you'll want to commit to memory. So it says remembering all these names and formulas is greatly facilitated by memorizing the common ions that end in -ate. Then you can either apply if it is an -ite ending or a per ending, per prefix. So you can have a per prefix and a hypo prefix in some situations. There is an expanded list with this that has the -ite endings and the per prefixes and hypo prefixes. I recommend just memorizing all of them and committing them all to memory. And I won't read all of these for you. You can just read through them on your own. Example 511, determine the formula of sulfurous acid. So we have two Latin endings. One of them is us, which is OUS, and the other is ic, which is IC. Of the two, the us is the lower, and the ic is the higher, and it applies to the number of hydrogens. So again, the strategy here, the us ending in the name of an acid indicates that the acid is derived from an oxoanion ending in -ite. The -ite suffix is the lower versus the -ate suffix, which is the higher. So one more time, us would be higher, or lower, excuse me. Us is lower, ic is higher, and those would be our endings. And then we also have -ite and -ate. -ate is higher and -ite is lower. And if you write that out a few times, then I think you'll have it all situated in your mind. The oxoanion must be sulfite, which is SO3 2-, so add enough hydrogen ions to make this neutral. So these are not charged. Our two situations would either be sulfite versus sulfate. Sulfite is the lower and sulfate is the higher. The formula here, to neutralize the -2 charge, we need two hydrogens. So we have H2SO3 is sulfurous acid. Sulfuric acid would be H2SO4, so it would have one more oxygen. And again, remembering these names is greatly facilitated by memorizing all of the common ions and all of the polyatomic ions that will end in -ate. And then again, as I mentioned, write out the endings. OUS ending, which is us, is lower. IC is higher. I like to think of that I in ick in higher, which also has an I. So you can remember that. And then with ite and ate, I know ite has an I, but ate, I think of like eating something and you're full. So that one is the larger of the two. So ate is going to be larger than ite. Next example, 5.12. Calculate the molecular mass or the formular mass as appropriate for each of the following. A, propane, and it gives us the molecular formula, C3H8. B, lithium hydroxide, LiOH. And C, barium acetate, Ba, C2H3O2. And then there's 2 all in parentheses there. While we're here, and before we go on, propane has carbon, which is a nonmetal, and hydrogen, which is a nonmetal. So this would be a type of molecular compound. And it's not tri-carbon, octa, hydrogen. It actually does use a common name. And there's a set of common names, and we'll get to these as we look at a handful of organic examples, specifically types of hydrocarbons that only contain carbon and hydrogen. But I'll leave that for later. The next one, lithium hydroxide. You have your hydroxide, which is a polyatomic. Lithium, which is a metal. This would be an example of an ionic situation. And then the last one uses acetate, which is another of the polyatomic ions, and then also uses barium, which is a metal. So this would be an ionic compound that uses a polyatomic ion. So just to be thinking about that. Now let's get to what this is asking. Calculate molecular mass or formula mass. This is really fairly simple, and most people can grasp this right away. So to figure out the molecular mass, all you do is look at the periodic table and find your atomic mass units, which is the bottom number underneath the elemental symbol, and then figure out how many you have of each of your elements in your molecular formula, and then multiply out and add all together. So let's take a look at those. So for the first one, propane is C3H8. So the molecular mass, we find carbon in the periodic table, which is 12.01. We have 3 of those, so they have this multiplier of 3. So you do 3 times 12.01, and then add to that 8 times 1.008. The 1.008 is for hydrogen, and then since there's 8 of those, 8 times that. So 12.01 times 3 plus 8 times 1.008, we come out to be about 44.09 atomic mass units. The formula for lithium hydroxide we saw was LiOH. We have 1 lithium and 1 hydroxide. Find lithium in the periodic table, which is 6.941. We add to that oxygen, which is 16, and hydrogen, 1.008. Sum all of those together, 23.95. You're probably thinking, oh, this isn't bad. I get this. This is pretty straightforward. And then for the last one, barium acetate. Barium, we find that is 137.3. And then in the acetate, if you look back, you have C2H3O2. That's all in parentheses, and there's 2 of those. The reason why there's 2, if you think about the charges, barium is a +2 cation. Acetate's a polyatomic ion that's -1. So to get the -1 to match the +2, we need 2 of it. And since it's a group, a polyatomic ion, the whole thing has a charge, we would put parentheses around it and then have the 2. Now what this means is that we have 2 times 2, 4 carbons, 3 times 2, 6 hydrogens, and 2 times 2, 4 oxygens. So we need to take into account the mass and atomic mass of 4 carbons, 6 hydrogens, and 4 oxygens. So there's our 4 carbons, 6 hydrogens, and 4 oxygens. Multiply and then sum all together, and we should get somewhere around 255.4. So that's all there is to calculating a molecular mass. One thing that you do want to remember is that you double check, make sure that you didn't miss any of the elements, especially if you have something with parentheses. Make sure you multiplied that through as I showed you with the acetate. And of course that you use the correct number from the periodic table. Like you use the mass of carbon if you're using carbon and not the mass of calcium. Let's look at 5.13. Lithium carbonate, formula here is Li2CO3, was the first mood-stabilizing drug approved by the Federal Drug Administration, the FDA, for the treatment of mania, that's right, mania, and manic depressive illness, also known as bipolar disorder. Calculate the percent composition by mass of lithium carbonate. Key thing here, we're going to use equation 5.1 to determine the percent by mass contributed by each element in the compound. So this would just be an extension of molecular mass, and then looking at how much mass does each element contribute to the overall mass as a percent. So shouldn't be too bad once you have a good handle on atomic mass. And then just remember that percent is part per whole. So for each element, we're going to multiply the number from the formula by the atomic mass from the periodic table. And then we don't want to end with just the fraction. We actually want to have the whole number percent. So of course we'll multiply by 100. So lithium carbonate, the whole thing all together, you would do 2 lithiums, 1 carbon, and 3 oxygens, just like we did in the last example. Add up the entire molecular mass, and that should come out to be 73.89. So for the percent lithium, the formula Li2CO3 has 2 lithiums in it. Lithium is 6.941, so you do 2 times 6.941. That's how much mass lithium is of the total. And so you'll do part per whole. And notice the whole is the same for each, which is just the total molecular mass. You multiply by 100, and that means that lithium contributes 18.79% of the lithium carbonate. For part B, you'll do it for carbon. There's just 1 carbon. So 12.01 divided by the total molecular weight times 100, 16.25%. And then oxygen. There's 3 oxygens in lithium carbonate. So 3 times 16 for the atomic mass units of oxygen. Divide by the total molecular mass of lithium carbonate times 100. And you get 64.96%. And since that takes up every element that's present in lithium carbonate, then these 3% should add up to 100. So not too bad. Just make sure you have a good handle on adding up molecular mass, and then just remember part per whole. I think once you work through a few examples of this, then you'll have a good grasp on it. So one thing to remember, make sure that your percent composition, the sum of all of it does add up to 100. And then remember that because of rounding, then it might be slightly more, slightly less. So don't be too worrisome about it if you're slightly above 100, like 100.45, and that just may come about from rounding. Okay. Next example, 5.14. Determine A, the number of moles of carbon dioxide in 10 grams of carbon dioxide, and B, the mass of 0.905 moles of sodium chloride. So we're meshing together a few ideas here, and we're leading into an area that is known as stoichiometry. The strategy is to use molecular mass, or molar mass, same thing, to convert from mass to moles, and to convert from moles to mass. We listed the numbers in the periodic table, those bottom numbers, as atomic mass units. Those are all equalities of what is the mass of 1 mole of each of those elements. So for example, carbon we know is 12.01 atomic mass units. That also means that 1 mole of carbon would have a mass of 12.01 grams. So when we were calculating the molecular masses, and you've practiced that, and we've also looked at the percent composition, we also are given a relationship of grams per mole. So the molar mass of carbon dioxide, you would just use 2 times oxygen, which is about 16, and then add to that carbon, which is 12.01. So you'd have 16 times 2 is 32 plus 12.01, and you get 44.01. The units are atomic mass units, or in this case, if we're using it as a conversion from grams to moles or moles to grams, the units can be grams per 1 mole of carbon dioxide. Molar mass of sodium chloride, you'd find sodium in the periodic table, chlorine in the periodic table, add up their atomic weights together, and you get 58.44 grams per 1 mole. So our solution here for part A, and let's remind ourselves what that question was, the number of moles of carbon dioxide in 100 grams of carbon dioxide. So we're starting with a mass of 100. And we want to set this equality up so that grams cancels. So we put moles in the numerator and then our mass of carbon dioxide in the denominator so that the grams of carbon dioxide cancels, in that you have grams of CO2 divided by grams of CO2 goes to 1, and we're just left with moles of CO2. So 100 times 1 divided by 44.01, we get something like 0.2272 moles of CO2. And then they started with 4 significant figures, and the answer also has 4 significant figures. Part B is looking at moles of sodium chloride. You can see the mass of 0.905 moles of sodium chloride. So this time we start with moles, but you'll notice the relationship is flip-flopped. And why is it flip-flopped? Well, that's so that moles will cancel. We don't want to cancel grams this time. We don't want to have moles divided by grams and times moles. It's not going to cancel out our units. So we need to cancel moles. So we need to have moles in the numerator in one place, moles in the denominator in another place. When you start with just a digit, again, you can think of it as being divided by 1. The 1 would be in the denominator, and then just this value would be in the numerator. So we have moles in the numerator here, moles in the denominator there. It's a happy world. We get those to cancel. We're left with units of grams of sodium chloride. Again, just like when you're working through conversions, make sure that you can cancel the units first, then put in the numbers. And as you practice, you can do it all at once. So 0.905 moles sodium chloride times 58.44 grams of sodium chloride divided by 1, we get 52.9 grams of sodium chloride. 3 significant figures here, so 3 significant figures in our answer. So one thing to think about, as I mentioned, just check your units, make sure they cancel. Those are very common errors where you just set it up and put the wrong ratio. You set it up upside down and the units don't cancel. So make sure that you get your units to cancel. Also, in both cases, a mass smaller than the molar mass corresponds to less than 1 mole of a substance. So that's just conceptually another thing that you can be thinking about. I'm going to go ahead and end the video here. We have just a couple more examples, and I'll do that in part 3.